Hi, everybody. We're here to talk about the fundamental theorem for line integrals. So we're in section 15.3, and in order to get psyched up for the fundamental theorem of line integrals, we're going to talk about the fundamental theorem of calculus back from Calc 1. Now, when you saw the fundamental theorem of calculus in Calc 1, was probably right as you were getting into integration. And one of the things that you were probably talking about early on was this new thing called an area function. And an area function was, something that, given a function like f here, an area function would give you the area underneath the curve up until some point. Ooh, I just totally crossed off half of A there, but yeah, I realize that it's all this area. And likewise, we could have an area under the curve for all the way out here to B. We call this one f of B. But once you're able to, find some area functions, which we learn are antiderivatives, we can find the integral from A to B, the area underneath this function from A to B, just by taking the difference of these two areas. So we've got the orange area minus the green area, and that's the fundamental theorem of calculus, part 2, in the normal context as it's introduced. So deviating from how it is normally introduced a little bit, let's go ahead and look at another context where, we've got the function and antiderivative relationship going on here. But over on the left, we've got a derivative and then, the original function here. So we still have derivative, antiderivative kind of a relationship going on. Still the same thing. But since this is written as f prime of x dx, what we can do is look at this in another way as the ratio of these differentials dy over dx. And, if you squint hard enough, maybe these dx's cancel, and all you're left with is an integral of a bunch of dy's. Let's think about what that might look like geometrically. Down below, the task would be, can we, figure out how much the y value changes from our starting y value to our ending y value. If you already have a function f, by far the easiest way is to calculate f of b and subtract f of a. That gives you a difference of y values. But what if you didn't have f? I'm just going to erase it for a second. What if you didn't have f, but all you had was information about the derivative? Then what you could do is, using your calculus thinking, you could add up a bunch of slopes. So that if for every, change dx in the domain, there is a corresponding, change in the range here. dy, every time, you're going to add on a little bit of y values, and that adding will change as the slope changes, but you're adding a bunch of slopes, and if you take the sum of all of these slopes, you hope that in the end you get the same answer. You've basically summed up all of the changes of the y values to get from this point to this one. Now, is it easier to add up an infinite number of slopes in order to get this change in y values? Or would it be easier just to calculate the y value at the end and the y value at the beginning and subtract them? Well, this one's obviously easier, right? And that's what we're going to do today for line integrals. So yesterday, we were doing the equivalent of adding up a bunch of slopes along the way. We were traveling along a space curve. I don't know if I have a good picture. Nah, not really. We were traveling along a space curve, and either we were adding up scalar values. We're adding up scalar values along the way. Either we had a scalar function that was determining kind of the height above our windy path, or we were going along that windy path and taking dot products with a vector field in order to get scalar values at each point. So we were doing more of the add up a bunch of things. And today, what we're going to be doing is learning how to go backwards, find the potential function, and actually just calculate a difference. Well, it'll be in z values for us, but this is a difference in y values. Okay, here's the fundamental theorem for line integrals, also known as the gradient theorem. Assume that f is a differentiable function whose gradient is continuous along a curve c, and that c is defined by a smooth vector function r of t. Then, along this curve, you can add up a bunch of dot products again. So this is over a vector field. We've got our vector field in green, and that's a gradient field because it needs to be the gradient of some potential function in order for this to work out. And then we're taking the dot products all along the way with the tangent vector along the curve. We were calculating these directly yesterday and making sure to parameterize our curve and make sure that our force field was also written in terms of that parameter, and then going through all the steps to actually figure this out. But what we're going to be able to do today, as long as we have a potential function for this vector field, we're going to be able to just subtract for this potential function f. I should write that there. We're just going to subtract kind of the ending point and minus the starting point, and we will get the value of the entire line integral in one easy step. Let's go ahead and take a look at our first example. Now, I've got a lot written here, and I totally could erase it and do it over again. Probably, yeah, I will. That's fine. That's going to be better. Because this is all a mess if you look at it all at once. Let's erase, Bye-bye. Bye-bye. Okay. So we've been doing this weird looking integral. We've got over a curve C, but y dx plus x dy, why do we have two differentials here? What does this even mean? Well, you can think of this as like the dot product already happened to some extent. What we would have seen yesterday is we would have had some kind of function parameterized in terms of t, and instead of looking at y dx and x dy, we would have had a force field that looked like y and x. So that would have been our force field. And we would have dotted that with the tangent vector. And the tangent vector, I mean, you could think of that as being yeah, I mean, the derivative of the x component and the derivative of the y component, what would be, oh, I need to do that in terms of, oh, yeah, sorry. dx dt and dy dt. Sorry, I forgot how I was going to write that. I needed to write it in terms of differentials. Um, but yeah, the idea here is that, if you do this multiplication, or yeah, this dot product out, you would get this as long as you multiply the dt's in so that the dt's on bottom actually cancel out. So this is weird. Imagine that the dot product has already happened. The cool thing that we're about to learn, and I might just go down there and show you right now. The cool thing that we're about to learn is that once you know the fundamental theorem for line integrals, and you've confirmed that you've met the criterion that you're working with a differentiable function who has a gradient, and yeah, your vector function is smooth. We're going to learn that if you are on a conservative vector field that has a potential function, these line integrals are going to be path independent, meaning that the specific path that you take through the vector field is not going to matter. You could take literally any path to get from one point to another, and they're all going to be equivalent. So that's about what we're going to do, and that's why we don't have more information about the parameterized path, is because it's not going to matter. If we keep going on this, though, and use the fundamental theorem of line integrals, what we would need to do is recognize that this vector y and x is the gradient of some function f. And what we would do is we need to figure out what that function f actually is. And so what we could do is, write down that the partial derivative of f with respect to x is y, and the partial derivative with respect to y is x. And we could think about, okay, if we go back up one step and take an antiderivative with respect to x, f could look like, am I crazy or did my pen just change shape? Anyways, we'll see. Antiderivative. Yeah. We're used to seeing this. Yeah, y is just a constant with respect to x. So yeah, the derivative there, or the antiderivative, would be xy plus possibly some function completely in terms of y. For this one. And then let me change the color here. And for this one, we would be thinking, okay, f of xy could be taking the antiderivative with respect to y. Again, it's going to be xy plus some unknown function of x. But in order to make these two things equal, it's fine to just set g of y equal to 0 and h of x equal to 0. And not, fuss about those extra constants or anything. And just say, oh, actually, a potential function that would work is x times y. And so, yeah, in order to solve this problem, using the fundamental theorem of line integrals, I've taken way too much time on this. I'm sorry. All we got to do is evaluate this. I don't know, maybe we go like this. xy from starting at 5, 0 and ending at 3, 4, this turns into be 3 times 4 minus 5 times 0, which is 12. So not a ton to do there, but we found a potential function for this gradient field. Yesterday, if we were to do that problem, we would have had to parameterize this path. I guess this says this is the part of the origin-centered circle of radius 5, starting at 5, 0 and ending there. So we would be going counterclockwise. And notice I didn't even make use of that in this problem at all. I didn't care about the path because we used the fundamental theorem of integrals. Yesterday, if we would have done this, we would have had to parameterize that path, and maybe we would have used, cosine and sine like we'd done before. Probably R of t would have been cosine t sine t to make sure, well, in fives, sorry. Yeah. Then we would have taken a derivative and put it here and all that good stuff. We would have, made the force field in terms of our parameter t as well. And then, kept going. And notice there's, a lot more steps here. We would have had to figure out that we end at the arctan of 4/3 when you're going around the unit circle and then end here. It was easier to do this with the fundamental theorem of line integrals. And that's always a great thing when you can do something easier in math. I mean, it's cool to know that at least that's possible. That's how we would have done it yesterday. Moving on. Next one. Oh, actually, not moving on. Going back and examining things geometrically. I just remembered, we didn't look at the GeoGebra thing for this at all. All right. So, I know that this is maybe not super exciting, but the idea is we're taking a line integral over a vector field, and the vectors just disappeared for some reason, and then now they're back. We're going along this path in this problem from a point A to a point B. We're given that the point A is 5, 0, and the point B is 3, 4. And we're going along a circular path. But notice how much clarity there is when I tip this thing on its side so that you can see the z values. I mean, what we would have been doing yesterday is going along this path and doing a bunch of dot products all the way and adding up all of those dot products along the way with the vector field and the tangent vector. But when we tip this to the side and we see, oh, point B is up there and point A is down here, and what's this blue thing? The blue thing is our potential function. F of xy equals xy. And so literally the answer here is, what is the difference in z values? The difference in z values, we started at 0, we end at 12. That's the end of the game. Like, that's it. So if you can find a potential function for your vector field, this fundamental theorem of line integrals is super useful. There's the 12 right there. And notice how going along this parameterized curve, I don't even know if I have any more curves in here. I mean, we could make some more, but if I'm starting at point A and ending at point B, notice that it doesn't make any difference at all if I start off by going over here, going all the way around here. As long as I'm starting at point A and ending at point B, the difference in z-values is going to be 12. And that's super cool. Yeah. So, yeah, that's the path independence thing I was talking about. All right. Example number 2. Now we're ready. Given a fluid velocity field defined by the gradient of potential function, this is the exact problem that was at the end of yesterday's class. This is example 5. So yeah, picture looked like this. Come on. And yeah, I mean, we let this go and taken dot products along the way. And those dot products got bigger as, those vectors got bigger. Anyways, instead of doing what we did yesterday, come on, computer, give me that. All the way at the bottom of yesterday. Oh, geez. Come on. This is what we did for the same exact problem from 0, 0 to 1, 1, 1. Take this dot product, have a parameterized curve, have a force field. Eventually you get 1 after doing that dot product. In this one, much simpler. Since we have the potential function x times y times z, we can just use that and literally put in f of 1, 1, 1 minus f of 0, 0, 0 and get the difference in y. Well, not difference in z values here, because this is a 3-variable function, kind of the difference in w values if you want to think about it that way. Yeah, the difference there is 1. Super cool. Yeah, let's keep going. Here we talk about the path independence of line integrals. Again, we have a continuous vector field defined on an open region D. A and B are 2 fixed points on that D. Yeah, 2 points. As long as you're going between those 2 points along any curve, this integral has the same value for every piecewise smooth path joining A and B. And we say that the integral is path independent. Yeah, so normally we would write line integrals this way, but if you're in the situation where any path is going to work, you can rewrite that integral as going from A to B there. So you could literally just put the ordered pairs A and B in there and that would be fine. Because the exact path doesn't matter. So here we're going to look at that having a conservative vector field implies that you have path independence. And then down here, we're going to see that path independence implies having a conservative vector field. Those happen, yeah. And I guess, those happen now if and only if. Yeah, I don't necessarily have proof for these listed, but yeah, we're going to be looking for conservative vector fields where we can find a potential function. This one in the middle talks about path independence and closed path integrals, so that if you are on a conservative vector field, and I don't know if you've heard this explained this way yet, but a conservative vector field is called conservative uh, for precisely this reason, that if you start at a point, go along some path, and then end up at the same point, that line integral will be zero. I mean, um, you could go back to the picture. Come on, computer. It's not letting me bring up Chrome. Here we go. Um, this one's better. Yeah. You can think, starting at A, you could take any path you want. If you end at A again, the Z value hasn't changed. The line integral would be zero. And this is important physically because, there are lots of things, lots of force fields in our world that are, I don't know, like conservative. Conservative meaning that while the force field might be able to do work, you wouldn't be able to make what's the word for it? Like an infinite energy machine out of it. Like gravity is a conservative vector field, or at least can be represented with a conservative vector field, because while gravity might act on an object, unless you are, changing the gravity field, you're not going to be able to like add energy to the system. I'm not a physicist, and that is horribly obvious. But yeah, what's the word? Conservation of mass and energy, all that good stuff. Things are conservative. It's not created or destroyed. Something like that. Oh my gosh, I am so embarrassed. That's the idea of conservative. It means that, properties are conserved. All right, that's why it ends up being zero. Let's keep going. Example number 3. Here we go. Function, vector field here, force field, f of x, y. Boom. Here we have a path from 0, 1 to 1, 0, defined by this function. And then here we have a path between those same 2 points, given by a different function. So one of them would be following this parabolic arc, and the other one would be going along the curve of the circle. Now, I guess in a later problem, we would show that these line integrals are not the same, meaning that the force field behind this is not a conservative vector field. And we wouldn't be able to use the fundamental theorem for line integrals or the gradient theorem to evaluate either one of these line integrals. So it would really be nice for us to be able to look at a given vector field and decide whether it's a conservative vector field or not. And generally we're going to do that by looking to find if it has a potential function, and we can use Clairaut's theorem to help us with that too. So if we were to, here we've already got the partial derivative with respect to x, and here's the partial derivative with respect to y. If we were going to find the mixed partial derivatives, what we would do is take this first part, that's the partial derivative with respect to x, and take its partial derivative with respect to y. And when we do that, we get a 1. If we take this part and take its partial derivative with respect to x to get the second mixed partial derivative, we get a -3. And we see by Clairaut's theorem, this doesn't work. geez, that's not right. You can't even read it. Oh, man. But yeah, there's not a potential function underlying this vector field. It's just a vector field without a parent. Okay, the component test for conservative vector fields here is really just operationalized Clairaut's theorem. So what we're working with here with this, this vector field is we've got a partial derivative with respect to x and a partial derivative with respect to y. So yeah, P is already the partial derivative with respect to x for some function. Q is already the partial derivative with respect to y for some function. So what we're doing here on the first part is testing, does f of xy equal fyx? And do those things equal each other? And here we're just working again with mixed partial derivatives, but here we're comparing between three variables, x, y, and z. And we're doing this case-wise so that we check all of our bases to make sure that they're all equal. Yeah, we're doing the same thing. It's Clairaut's theorem. For example number 4, we want to show that this is not conservative. So yeah, we take those partial derivatives not conservative by the component test, Clairaut's theorem for the mixed partial derivatives. Example number 5. Yeah, let's erase this. Oof. Part of me is sad to see this go, but we got time. Find a potential function for this force field F, if it exists. So one thing that we could do real quick to test and they call this the component test, would be since we've got the partial derivative with respect to x and the partial derivative with respect to y and the partial derivative with respect to z, what we could do by this component test, because now we've got 3 variables, is we could go through each one and make sure that the partial derivatives actually equal each other. So in this case, we would be looking for does, let's go xy equal yx. So we're looking at these first 2. We take a derivative of this first one with respect to y. And y only shows up here in the first term. E to the x is acting like a constant. So if we take the derivative, we just get e to the x on the left-hand side. And on the right-hand side, we go here. And if we take this partial derivative with respect to x, we get e to the x, because that's its own derivative. So for that first part, we check it off, it worked. Once that one works, you might just want to start going in and figuring out, hey, let's try to find a potential function because it probably exists. If one of these works, you can go through and find the other ones too. But yeah, it's going to get boring. Essentially, what we want to do is find this potential function. We want to treat this as the gradient of some function f, and what we're hoping for is to find, let's see, let's go blue, that if we take an antiderivative of y e to the x plus z cosine x with respect to x, and set that, we want all of these to be equal. Green. Integral of e to the x minus z squared dy, and that could be equal to integral minus 2yz plus sine x, dz. We want all these antiderivatives to be equal because we're undoing the partial derivatives that were already done. And hopefully here we'll find, instead of having the gradient, we'll find a value for what the actual original function was. Let's go ahead and try to do this. It could be an adventure. If we take an antiderivative here, that's just a constant, so it's just going to chill. So this becomes y e to the x for that term. And then antiderivative of cosine is sine. So this becomes z times the sine of x. And then we possibly could have some function, let's call it h, or well, let's call it g. We could have some function of strictly y and z that just got deleted when we took the partial derivative with respect to x. So that one's accomplished. Now let's look at the green one. Here we are taking the antiderivative with respect to y, and both of those look like constants with respect to y. So I'll just go ahead and write it like y times e to the x minus z squared y for our antiderivative. And this potentially could be missing some function of x and z that just got deleted when that partial derivative was taken. Okay, last one. We're taking the antiderivative with respect to z now. We would get yz squared for that first term. And then sine of x becomes z times the sine of x. And possibly there could be some function ghi. Let's use j of x and y that could be there. Let's go ahead and look at what we've got. We have y e to the x in both of those, so that must be the same thing as jx of y over here. Here we've got z times the sine of x. We've got h of x and z there, and we have z sine of x here. The last one, let's go purple. Some function of y and z. That function of y and z is minus z squared y. And this one's minus z squared y, although I forgot to write the minus sign earlier. Cool. So yeah, notice now we've got a function for f here. So we have our potential function and we're good to go. We just needed to undo the partial derivatives in the gradient that was already taken. Cool. Next one, example 6. So here we have this line integral where all of these parts are what we just worked on. This is the partial derivative with respect to x. It's showing up right here. Partial derivative with respect to y, partial derivative with respect to z. And what we found was that this was a conservative vector field that has a potential function. The potential function is, right here. Any one of these, I mean, I guess, I never really summed it up all into one. Y e to the x plus z sine x minus z squared y. There's our potential function. And yeah, using the fundamental theorem of line integrals, all we've got to do is take that difference, evaluated the endpoint minus the starting point, and all of the paths in between those 2 points would be equivalent. And you end up getting the value -8 for that line integral. So it's just an application of the fundamental theorem for line integrals. And that's super cool. One more, and then that's the end. So there's that. I'm moving on. Example 7. Final one. I think we have the potential just to talk through this one. All right, example 7. We're given this line integral again in a situation where that dot product thing has already been expanded. The dot product has been taken. What we really need to identify is that this is the x component of the gradient, this is the y component of the gradient, and we need to come up with a potential function. So when we're finding the potential function, this is our gradient, and we would be integrating this first part with respect to x and the second part with respect to y. We get down here and see this is minus x squared y plus possibly just some function of y. Here we get 3y minus x squared y plus possibly some function of x. But the things that actually match are the minus x squared y's, and 3y there is actually as a function of y. So this is our potential function, minus x squared y plus 3y. And then after figuring out the potential function, we just apply the fundamental theorem of line integrals and do ending point minus starting point. Oh, and we know which one is which because there's this little arrow right there in the middle. So we're starting off at 1, 0, and we're ending up at 0, 1. But yeah, you put those points as the x and y values into your potential function, subtract, and get 3. That is the difference in z values that you would see for this function graphed. Cool. All right, well, thanks for sticking with it. I guess this is going to be a little bit early, but yeah, if you guys have any questions, go ahead and, talk about that amongst yourselves. And otherwise, I'll see you tomorrow for an activity. All right, talk to you later.